Hello and very good morning, very good evening for everyone joining with us today, and wish you a very happy new year from the team NcodeX. Today we have Pramodh, and you may have noticed we're changing a schedule a little bit than to our previous schedules. That's because Pramodh is joining with us from Alberta in a late night. So thank you very much for your commitment and joining with us and agreeing our invitation to do the next episode of the PhD Talks by NcodeX episode 5. So giving a bit of background on Pramodh. So he's a PhD student in University of Alberta in Canada, and he has completed his master's degree in University of Victoria, British Columbia, and bachelor's degree in Carleton University, Ontario. So today he's giving a very interesting topic on discovering quantum states of matter, which has a lot of applications, and I will hand over to Pramodh to continue.
Wonderful. Yeah, thank you so much, Rooney, for the introduction. Let me get my slides going and turn on captions if I can. Okay, so give me 1 second to, and yeah, the captions keep turning off sometimes, but it's okay. Let's see if this works. Okay, so hello everyone, and thank you, Rooney, again for the introduction, and NcodeX for the invitation to give this talk. I kind of made a resolution last year to interact more with the Sri Lankan side of the scientific community, and what better time to fulfill that than at the start of this new year. I'm also kind of very excited to give this talk because I'm pretty sure this is the first talk I've ever given where I don't have to anglicize my name. So I usually starts my talks by saying like, hello everyone, my name is Pramodh Senarath Yapa, because I don't want people to butcher my name in the question period. So I don't think there's much of a chance with that today. So for the first time ever, I can say, hello everyone, my name is Pramodh Senarath Yapa. And as you can see from the title, I'm going to be telling you a little bit about the quantum states of matter. Now, you may already know a little bit about the normal classical states of matter, but things get way more interesting when you throw quantum mechanics into the mix. Now, these pictures that you see here are actually showing 3 different quantum states of matter. And in fact, this figure right here in the middle is from one of my papers that got accepted for publication back in December and should be out in print in just a couple more days. It's about a newly discovered quantum matter state called a superfluid crystal, which behaves like both a solid and a frictionless liquid at the same time. So my supervisor, the postdoc in our group, and I were able to construct the first ever theory explaining why this brand new state of matter appears and how it behaves. So needless to say, I'm very excited about it, and I'll hopefully tell you a little bit about this at the end of my talk. While the bulk of my talk will be on introducing these states to you and telling you why they matter. So you can see from this bar right here at the bottom that I'm doing my PhD in condensed matter theory, which is probably not a very well-known discipline of physics in the public domain. But it's actually the field that the majority of research physicists in the world work in. Condensed matter suffers from a bit of a kind of a marketing problem, and having a very opaque name like condensed matter physics doesn't really help. So I think for the purposes of this talk, you can consider me a low temperature physicist. And I do all of my low temperature physics at the University of Alberta, which is in Edmonton, Alberta, Canada. And once you have an idea of where Edmonton actually is, what I do and where I work has a funny kind of connection, which is the source of a joke I use quite often. So I'm going to let you in on that joke by showing you where Edmonton is. So here's the globe. Edmonton is right here. It's the most northernmost city in North America, which has over 1 million people. And this is Edmonton. This is kind of like the North Pole. So as you can imagine, it gets very cold over here. This was the weather forecast for the last week here. The last 10 days, the highest it ever got was negative 25 degrees Celsius. The low was a negative 40 degrees Celsius. And this is what you look like when you spend 10 minutes outside in those temperatures. So my go-to joke here is that Edmonton makes it very easy for me to be a low temperature physicist because I can just walk outside and start doing research. Unfortunately, reality isn't that kind. These temperatures aren't actually low enough for what I do. But what it does is provide an excellent way to demonstrate the normal or classical states of matter, which are solids, liquids, and gases. So here I am on one of these minus 30-degree days, blowing soap bubbles outside. And what I love about this GIF is that it shows all of these three classical states in one. So what's inside the bubble is air, which is of course a gas. The bubble itself is made out of water and soap, and it's a liquid, but you can see in a split second, it freezes and it turns solid. Now, this is what is called a phase transition. One state of matter changing into another as you change something in the environment. In this case, the temperature of the soap bubble starts dropping, and just when it hits about 0 degrees Celsius, its properties change very suddenly and drastically. Goes from being a liquid to a crystalline solid. Now, this kind of sudden change in property is what low temperature physicists look for when trying to discover new states of matter. So with this definition of a phase transition in mind, we can ask, are these three or really four states of matter the only ones which exist? I say four because some people include plasma as one of these four canonical states of matter. And the question remains the same. Is it true that it's only these four that can exist? And the only way we can claim that these are the four states of matter is if we confine ourselves to a few things. One, if we confine ourselves to the properties that we can detect with our senses. But of course, we know many things in nature lie beyond kind of the threshold of what we're able to see or touch. And there are some properties we just simply don't have the sensory organs to detect. Another thing that confines us here is the pressure ranges and the temperature ranges that we live in. There's a very narrow band of these, which we as humans are able to tolerate. And these four states of matter are simply the ones which show up in this very narrow band. But of course, this is a very bad way to do science because ultimately science is about going beyond our subjective perceptions and trying to learn more about kind of the objective nature of reality. So to give you a couple of concrete examples of what we miss when we constrain ourselves to our subjective viewpoints, magnetism is one. A magnet is actually a state of matter which follows this above definition of a phase transition. Magnets lose their magnetism suddenly when warmed above a temperature called the Curie point for Marie Curie. But magnetic forces aren't something that we experience firsthand, so then we don't think of it as a normal state of matter. When going beyond normal pressure and temperature ranges we're used to, something we miss is something called a supercritical fluid. This is a state where there's no distinction between a gas and a liquid. So in this GIF, they are changing the pressure and temperature of liquid carbon dioxide. So at the start of this GIF, you can see a clear separation of the liquid at the bottom and the gas at the top. So liquid, gas. But at a certain point, as they change the temperature, as they change the pressure, this boundary suddenly vanishes. This is the supercritical phase of liquid carbon dioxide. And so with these, hopefully I've convinced you that there are more than four states of matter, as long as we kind of open up our mind to the wider world, and that we can discover new states of matter by exploring different pressures or temperature regimes and using sensors that go beyond what we can see or touch. Now, since I am a low temperature physicist, I'll be telling you about what we can discover as we cool way, way, way down below what we're used to, but also really way below any temperatures that have existed anywhere in the universe. Really, actually, in the universe, and I'll tell you exactly why I know that a little bit later. But for now, let me tell you about some quantum states of matter. And specifically, I'll be telling you about a couple of these, superconductors and superfluids. These are phases of quantum matter which show up close to absolute zero. And to start you off on this journey, I'm going to tell you about a Moore's law-like pattern that's cropped up in the field of low temperature physics. Now, for those of you who haven't heard of it before, Moore's law is an observation in computer engineering that the number of transistors on a microchip have increased, have doubled every 2 years since the 1970s. So here is a microchip on someone's finger, and this graph is plotting the number of transistors. So the y-axis is plotting the number of transistors on a microchip. You may notice this axis is logarithmic. So the values go from 1,000 transistors at the bottom here up to 5 million here, and then 50 billion transistors right at the top. And the x-axis here is time, going from 1970 and ending in 2020. And you can see this clear trend of doubling every 2 years. And this has nothing to do with low temperature physics. I'm simply telling you this as there is a similar trend in cryogenics or low temperature physics, which has not reached the same level of fame as Moore's law, but in my opinion is way more spectacular of a pattern. So the similar law in physics is that the lowest temperature achievable has decreased by a factor of 10, roughly every 15 years since 1878. So this graph is something I pulled from an article published in 1981 in a magazine called Physics Today. And so even though this starts at 1878, it actually ends at 1981 because of when it was published. And the y-axis here is showing the temperature in Kelvin. And this is logarithmic as well, stretching from 1,000 degrees Kelvin up here down to 0.0001 Kelvin right at the bottom. So for everyone not familiar with the Kelvin scale, room temperature, or about 20 degrees Celsius, is about 293.15 Kelvin. So that's about here in the scale. And the conversion from Celsius to Kelvin is pretty easy. You just subtract 273.15 from the Celsius value, and you have Kelvin. So the lowest temperature you can achieve is defined as negative 273.15 Celsius, or 0 Kelvin. This is absolute zero. So you can see from this pattern of data points that unlike the actual Moore's law, which is kind of like flattening out over the last couple of years, this has been going strong since 1878 till at least 1981. Now, of course, a natural question you may ask is, how has this pattern fared over the last 40 years? And actually, just because of this talk, I decided to kind of dig into this question and update this plot myself. And in a stroke of good fortune, just a month ago, the low temperature record was broken with a temperature of 38 picokelvins achieved. So I knew I had at least one data point to add in, and so I made this graph. So let's take a look at this graph till the end of 2021. So these points, all the way until 1981, are the exact same as the previous plot. And these data points are the ones I added in. And as you can clearly see, the trend in low temperature records have actually accelerated over the last 40 years. It's even going further than a factor of 10 increase every 15 years. So the 2021 record, if this old trend was followed, would have been 1 microkelvin, which is this point over here. But the latest data point in 2021 was actually 38 picokelvin. So this is 100,000 times colder of a temperature than predicted by this earlier trend line from 1878. So as I said earlier, we are achieving temperatures colder than anywhere in the entire universe. This is not an overstatement. It's actually an understatement, because the coldest place in the universe is this place, coldest place in the universe outside of Earth is this place called the Boomerang Nebula, which sits at a fairly chilly 1 Kelvin or negative 272.15 degrees Celsius. Now, we know the rest of the universe is at an ambient temperature of about 2.7 Kelvin because of something called the cosmic microwave background radiation. This is the remnant of heat left over from the Big Bang. And as you can see from this line over here, this is where 1 Kelvin was surpassed. And this happened back in the 1920s. So the temperature record for the coldest place in the universe has been held by Earth for the last century. And, all of this is pretty nuts, but why we care about low temperature physics or low temperatures is that they can be used to create quantum states of matter. So what are they? So I'm just now going to walk you through some of these historic discoveries by pointing them out as data points on this graph here. And we'll start with superconductors. Now, the year is 1911, and this man right here, Kamerlingh Onnes, who is a Dutch physicist, had just discovered a way to cool helium down until it became a liquid. And with this discovery, he just started throwing in whatever materials he had into the liquid helium and seeing how they behaved. So on this fateful day, he put in the element mercury, which is a solid at these low temperatures, and measured how current would flow through it. He produced this graph over here, which shows the resistance of the mercury to electrical current, and it kept dropping until it reached about 4.2 Kelvin. And then suddenly, it vanished, dropped completely to zero. Now, this is, as we kind of discussed previously, a hallmark of a phase transition, a discontinuous change in the resistance while smoothly changing the temperature. So he had just discovered the first superconductor, a material which can conduct electricity with zero resistance. So you can transmit current with perfect efficiency using these materials. Now, after this discovery, it was found that many materials and ceramics became superconductors at low enough temperatures. So what you see here in this picture, in this GIF, is another magical property of superconductors. They levitate when placed in a magnetic field. This specific superconducting material is called YbCO, or yttrium barium copper oxide. It's what's known as a high temperature superconductor, which becomes superconducting at liquid nitrogen temperatures, which is around negative 200 degrees Celsius. So not really high temperatures. Now, of course, the holy grail for the entire field of superconductivity and low temperature physics is finding a room temperature superconductor. And we can understand why this is a big deal. This would revolutionize power transmission, as we could deliver electricity anywhere without any losses due to heat. I think currently we waste about 40% of heat generation as heat in power lines along the way. Now, I will mention that there was a lot of media coverage around a potential room temperature superconductor just last year. And interestingly enough, it was an experiment done by a Sri Lankan, Professor Ranga Dias at the University of Rochester in New York. But it's a bit of a controversial claim, so I wouldn't get too excited. So one, although the temperatures are near room temperature, the pressure required for this material to become superconducting was higher than at the center of the Earth. Secondly, a lot of people, including one of my supervisors, think that his experiment is completely wrong and that he's just making a mistake. So only time will tell if there's a legitimate discovery, but it's an interesting Sri Lankan connection nevertheless. Let me move on to talk about a different quantum state of matter. So we're jumping forward in history a little bit further up to the year 1938, where superfluid helium-4 was discovered. So in 1938, Kapitsa in Moscow, and independently, two Canadians, Allen and Meisner at the University of Toronto here, both discovered something interesting when they tried to make helium-4 flow through a very small space. So they checked how quickly liquid helium would flow through a capillary or a very tiny tube. So you can get information about how thick or viscous a fluid is by using this velocity measurement. So you can think about how easily water flows through a straw compared to something like a thick milkshake. The velocity of the milkshake would be much slower, and that tells you about the viscosity or the thickness of that substance. So this here is a plot from the original Allen and Meissner paper. They're plotting the velocity of the fluid on this y-axis here, and the velocity of how quickly the fluid would flow through these capillaries. So at temperatures above 2 Kelvin, they found very little flow through the capillary. So it's this line over here. And this makes sense because at temperatures between like 2 and 4 Kelvin, helium is just a normal liquid, which has actually the same consistency as olive oil. So it's like trying to slurp a very thick milkshake through a very tiny straw. It's not going to happen. So what was interesting is when they cooled it below 2 Kelvin and something very strange happened, the liquid helium would just flow effortlessly through these tiny millimeter-sized capillaries, indicating that the liquid helium had turned into superfluid helium. So here's a GIF from a great YouTube video. You can check it out yourself, showing this transition from normal liquid helium to superfluid helium. So in this GIF, the moment when this liquid stops boiling is when it turns from a normal liquid to a superfluid. And how you know this is the bottom of this container is a ceramic, which has micrometer-sized capillaries. This is like 1/100th the size of a human hair. So you can think of these as tiny little tubes that normal liquids can't flow through, but the instant that the liquid helium turns into a superfluid, it starts dripping down through the bottom of this millimeter-sized holes in the ceramic. So very amazing property that superfluid helium has. Okay, so I talked to you about these two different quantum states of matter that were discovered a while ago, but a natural question you may ask is, why should we care? And there are many good answers to this question. I'm going to focus on just one, which is talking about quantum computing. Now, quantum computing is a huge field, both on industrial and academic level. And it's picked up an enormous amount of momentum over the last few years. So let me give you a quick taster of this connection of quantum states of matter to quantum computing, and also what quantum computing has the potential to do in the future. So let me actually start with a classical computer, which is what everyone is using today to watch this talk, to watch your YouTube videos. And the basis of classical computation of normal computers is the transistor. These are the same transistors I mentioned at the beginning of my talk when bringing up Moore's law. And a transistor is a fairly simple device. It has these 3 prongs of wire, which are the only things we really need to focus on. We're going to call these the source, the gate, and the sink. And the transistor is essentially a tap or like a faucet for electricity. This gate wire just stops, it controls whether the tap is on or off. When it's off, electricity that's flowing through the source meets the gate and can't flow through, just like water can't flow through a faucet. When it's on, the electricity goes through the source, it goes past the gate and flows out into the sink. So really, this is just an on-off switch. These are what represent ones and zeros in your computer. This is the whole basis of digital computation, a whole bunch, billions of these transistors either being ones or zeros inside your computer. Now, the analogous component in quantum computers is called a SQUID, which stands for a superconducting quantum interference device. Now, I should say that superconducting quantum computers aren't the only way to build a quantum computer. There are ways to build them using superfluids and a bunch of other quantum states of matter, but I'll focus on this superconducting one for now. Now, the SQUID is simply a loop of superconducting material, like aluminum. So a loop of aluminum wire. And the ones and zeros are encoded in this by checking which way the current is flowing in this loop of wire. If it's flowing clockwise, it's a 1. If it's flowing counterclockwise, it's a 0. But where quantum mechanics enters this is that quantum mechanics allows current to flow both counterclockwise and clockwise at the exact same time. So if you ask what's the state of this bit of this loop of wire, well, it's both a 0 and a 1 kind of at the same time. And this turns out to have enormous implications for how you can process information and improve computation time. And the way we can quickly understand this is by talking about logical gates. Computation is simply taking these sequences of zeros and ones and then manipulating them into a different sequence of zeros and ones. So for example, you can think of taking this 0, 1, 0, 0, and then doing something to it, so it turns into 0, 1, 1, 1. Well, this manipulation is done through logic gates in normal classical computers. Logic gates are simply just these kind of devices that have inputs and then they have outputs. And for an example here, an OR gate is something that takes in 2 inputs and has 1 output. If you give it 2 zeros, it gives you back a 0. If you give it 2 ones, it gives you a 1. And this kind of table summarizes that aspect of it. A NOT gate is another example of a logic gate. It has 1 input. It just kind of gives you the reverse of whatever you put inside it. And really, you chain all of these logic gates together, and you are able to do any kind of manipulation on a sequence of zeros and ones that you want. And this series of logic gates, putting a whole bunch of them in a row and having them act on zeros and ones after another, are what algorithms are. At the end of the day, when you're writing code, you're implementing algorithms that turn zeros and ones into different sequences of zeros and ones. Just mathematically, you do this thing through linear algebra. Don't get intimidated by this. All you really need to understand is that you can represent these ORs, all of these logic gates, using mathematical forms called matrices. They're just like cupboards that you can put numbers in. You can just put zeros and ones wherever you want. So for example, a NOT gate would look like a 2x2 cupboard where you can put zeros and ones in them. So the thing to notice about these classical gates is that these have only zeros and ones in them. So there's a classical NOT gate, there's a classical C NOT gate, and they only have zeros and ones inside. This guarantees that the outputs are also zeros and ones. Now, this is kind of similar to quantum computers, but different in one way. The gates that exist in quantum computers are very different. They are not constrained to have just zeros and ones in them. So there's this thing called a Hadamard gate, which has -1s and square root 2s in them. There are sometimes imaginary numbers in them. And when you act on zeros and ones with these gates, you get some really strange outputs. Now, this is some entirely different mathematical language than you can achieve using these classical gates. And what quantum gates do is they give us this new mathematical set of tools that can develop new algorithms that may work better than their classical counterparts. So we think about this, turning these zeros and ones into another sequence of zeros and ones using a bunch of classical gates. There might be a way to use just 2 quantum logic gates to do the exact same computation. So you'll be able to do stuff much faster using quantum computing than you would do classical computing. Now, we are at kind of the baby stage of quantum computing as a field. So it's very hard to predict exactly how this will pan out. But there is a lot of exciting work being done on the development of quantum algorithms. Okay, cool. That was kind of the end of the bulk of my talk. I just want to spend now a quick few minutes talking to you about this kind of research that I just came out with over the last year. This is about a new state of matter that we helped characterize over the last year called a superfluid crystal. And it is a state of quantum matter that behaves like both a solid and a liquid at the same time. So I'm just going to take only like 2 or 3 more minutes just to run you through this idea really quickly because I think it's super neat. So superfluid helium-3 is actually a rare, helium-3 is a rare isotope of helium. Only 0.00013% of all helium on Earth is helium-3. The rest of it is helium-4, which I kind of talked about earlier. And really, it took a long time for physicists to have enough helium with them to experiment with them. And in 1972, superfluidity was discovered in helium-3 by Lee, Doug Ostroff, and Richardson. But this was at a temperature that was 1,000 times lower than helium-4. Now, the fundamental reason behind this is that there's a quantum mechanical reason that helium-3 actually needs to pair up before it can become a superfluid. And this extra step of pairing up before it can become a superfluid means that it's much harder to achieve the superfluid state. And so the transition temperature for superfluid helium-3 is actually in the millikelvin range, while it was only about a Kelvin in helium-4. So there's a phase diagram of helium-3, and you can actually see two different colors on there. It's because this exact same pairing mechanism allows there to be different types of superfluid in helium-3. So this red is just called superfluid phase A, and this is just called the superfluid phase B. They have slightly different properties, but at the end of it, they both can flow without any friction, without any viscosity. And this, for the longest time, was thought to be the end of the superfluid phases of helium-3. But in the 2000s, physicists began to wonder about whether you can actually make a new phase of superfluid helium by actually making it flow through very tiny spaces. I'm talking about on the order of 1/100th of a human hair, a micrometer length scale. Can you make something new show up? And so a group here at the University of Alberta over the last couple of years did an experiment that was looking at exactly that. So they took these, they essentially made a superfluid helium-3 sandwich. They confined the superfluid between two quartz sheets to a thickness of about 600 nanometers, and they checked out what was happening to the superfluid. And what they actually found was this new superfluid phase would show up in between these well-known A and B phases. So this gray stripe that appears in the middle. So I got to help out a little bit on the theory side of this paper, but really this was their experimental achievement. We got a little bit of press. It was a great little initial step to understanding this phase. But as soon as our group saw this result, we thought that there was a really interesting theoretical thing going on there, where this new gray phase could be something called a superfluid crystal, a new state of matter which could behave both like a solid and a liquid at the same time. So we got to work on that. And to understand why we're thinking this, we need to really kind of understand what makes a solid and a liquid a liquid. And at the end of the day, what the distinction here is patterns. Solids show patterns, while liquids do not have any patterns. And you can intuitively kind of understand this from this kind of ball and stick model that we have understanding of solids. Solids stay stuck in very ordered, rigid structures, while liquids are, jostling about. There is no fundamental order to them at all. So what we discovered is that the pairing of the helium-3 atoms, it allows them to move around like a liquid that can flow without friction, but at a larger length scale, it would start to show density patterns that looked exactly like what you would see in solids. And then we were able to predict this. So this is what we did in our new paper. We constructed a theory of this superfluid, and we were able to produce a phase diagram actually that matched the experimental one very closely. And even cooler, we were able to predict exactly the kind of patterns that would show up in this superfluid. And you can see there's not just one pattern I'm showing here. I'm actually showing you 9 patterns here. And the reason behind that is also very cool. Quantum mechanics does weird things. And it turns out that you can actually see these 9 different patterns at the same time in this superfluid crystal, depending on how you measure it. This is the fundamental kind of like wave particle duality nature of when you measure it, you see something different. Same thing is showing up here in the superfluid. So this is where we're at with kind of characterizing this new kind of state of matter, which is both solid and a liquid at the same time. We think there is a lot of more fundamentally interesting things going on in this state of matter, but we are working on that right now. And hopefully in the next couple of years, we will be able to tell you a little bit more about the properties of this really cool state of quantum phase. And with that, I'm going to wrap up my talk. Let me just quickly summarize what I talked to you about today. I started telling you about temperatures near absolute zero and how these can lead to new states of matter, which you can call quantum states of matter. Specifically, I talked about superconductors, which are these materials which can carry electricity with zero resistance. They also exhibit this cool magnetic levitation effect. And I also talked to you about superfluids. These are substances that can flow with zero friction. So if you take a cup of superfluid, give it a stir, it'll create a little whirlpool that'll flow forever without ever stopping. All of these properties only and solely due to quantum mechanics. Now, these states of quantum matter can be used to build quantum computers, which could potentially revolutionize computation. And then finally, I talked to you very quickly about this new research I did on superfluid helium-3, which is a substance which behaves like both solid and a frictionless liquid when it's squeezed to a nanometer length scale. So this is a new state of matter that we call a superfluid crystal. With that, I just want to thank my supervisor, the postdoc in my group, Professor Joseph Macheco and Dr. Rufus Boyack, who did a lot of great work in allowing me to do these kind of calculations. Of course, Professor John Davis's experimental group, who did the real, getting down and dirty kind of in the lab work that allowed us to make these kind of theoretical predictions. And with that, thank you for listening, and happy to go into the question period now.
Thank you very much, Pramodh. That was an excellent talk.
Thank you so much.
Very interesting. And you had quite exciting outcomes as well. So thank you for sharing your new inventions, and we hope you will find a lot of uses for your inventions, and we hope it will drive a whole new pathway for your research.
Thank you so much. Yeah.
Right. So if anyone's got any questions, by all means, you can drop in the chat, or you can put a comment in Facebook. Meantime, so I was kind of excited about your superfluid crystal. So
Cool.
I know
Yeah.
in the helium-3 superfluid, you talked about the Cooper pair, and then and you said there could be 9 different states, and it's observable at any time. So I was wondering, what factors could affect this different states? What do you think? I mean, is it something you've already observed, or something that needs to be discovered? Or, I mean, so the subatomic particle behavior and how that would affect the formation of the superfluid crystal from the helium-3. What do you think?
Yeah, so these are questions that we still don't really have answers to. We were able to, create a theory that gives a hint of what it would look like. At the end of the day, the experimentalists have to go out there and find this. The problem is, these are very hard experiments to do. You have to cool to near absolute zero, and then you have to do some interesting things to actually observe if there is now crystalline behavior. So to help the experimental colleagues, what I'm doing right now is calculating an experimental signature. Like, what can you do in your experiment to tell you exactly if you are seeing a crystal and exactly what the crystal structure that you are seeing. So this is a different calculation than, coming up with the theory. Now we're kind of calculating the consequences of the theory that we came up with. So I'm hoping to do this within the next month or so, and then I'll talk to my experimental colleagues. It'll take them a long time to work on this experiment because it is a very hard experiment to do. But there's this kind of back and forth that'll happen over the next year, and hopefully we'll be able to observe this actual the superfluid crystal state and get a validation of our theory. That would be nice. There's also the possibility that we're completely wrong, and this is the risk you run into when you do theoretical research.
Absolutely. Maybe a bit of statistical mechanics, and that could help as well.
Yeah, so it's very interesting. Like in physics theories, you can apply different tools. So statistical mechanics is a tool that you can use. Sometimes it's very hard because you're now trying to keep track of these billions of particles at the same time. The tool that we use to, predict this new superfluid crystal phase is a different tool that looks at average quantity. So we're not talking about individual helium atoms at all. We're kind of considering a density of helium atoms, and then that's what we're using to construct our theory. But it is a very good next step to now think of what is the next detail that we can put into our theory to make it more sophisticated, and that's actually working with helium atoms at that kind of microscopic scale. I would call my theory a mesoscopic scale, which is this kind of intermediate length scale theory, and then next step is a microscopic calculation. That's something that'll take kind of a lot of learning on my part to do, and probably another couple of years. And this might be a kind of end of PhD kind of calculation.
Well, good luck on that. We looking forward to hear any of your new theories coming up. So while talking about the future, so in the last 40 years, you talked about we've achieved 38 picokelvin. So that's interesting. Mm-hmm. So for someone who is willing to get into this field, is there any prediction you can make how far it would go?
Oh, okay. So this is something I left out of my talk, but you can go through the literature and find failed prediction after failed prediction. Everyone's like, this is the ultimate limit. And then 2 years later, somebody goes like 10 times colder than that. And then everyone's like, oh, okay, so somebody did that, but this is now the ultimate limit. And then like 3 years later, that's broken. So like, I am not going to make any predictions at all because that is doomed to fail. Every single prediction made by every single low temperature physicist has been destroyed over the last 40 years. I'm just excited just to see where the experimentalists can do this. I'm also not an experimentalist. I don't actually know what it takes to get to lower and lower temperatures. I'm just excited about all the new things that we can see by going lower and lower. There is an infinite depth to low temperatures that we can go to, and probably an infinite depth of new states of matter that we can discover as we go lower and lower and lower. So I'm just waiting and just eagerly taking anything that the experimentalists can deliver with their amazing cryogenic advances.
Is it mostly accidental, like every other?
I think I would be insulting experimentalists if I say it was accidental. I think there is a very good luck aspect to getting to these low temperatures. You need a healthy dose of good luck, but I think it also is this kind of taking earlier techniques, refining them, and then combining techniques from different areas that you'll never think about. So in my graph that I made, I showed this 2021 dot that lay perfectly on the earlier prediction graph, and then one dot that was 100,000 times colder. One prediction was using just a singular way of cooling things down. The one that went 100,000 times colder than that was using 3 different types of cooling all at the same time, which made it super sophisticated. One, they used laser cooling. So they get a cloud of atoms, they shot lasers at it, and somehow that actually makes the atoms colder. Then they put in a magnetic trap, and that takes out even more energy out of it. And then they took it up a 200-meter tall tower, and they dropped it. And during this kind of free fall stage, the microgravity environment allowed the gas of atoms to expand. And so they're using optical, magnetic, and gravitational cooling methods all at the same time to achieve this. So it's like thinking of these like wild ways to achieve things using a whole bunch of different techniques kind of on top of the other. So you need to get sophisticated equipment, but you also just kind of need an imagination to say, hey, we're going to take our big laser and then we're going to put a magnet in it, and then we're going to drop the entire thing down a tower. And it's like, who would have thought that would let you get to picokelvins? But apparently it worked.
Excellent. So talking about mad science, there are a lot of for future. So for anyone interested in pursuing similar field, would you like to talk about the innovation aspects of this? Because at NcodeX, we always promote innovation thinking 50 years or more ahead, and trying to find sustainability. And we also talk about interdisciplinarity, how we can use one field into other fields. So what is your opinion on this topic?
So I would say if anyone's kind of interested in being a physicist right now, condensed matter physics is absolutely what you should go into. I think when I was kind of growing up wanting to be a physicist, I just like looked at Stephen Hawking and I was like, "Ooh, I want to study black holes." And then like CERN came up with their particle collider. I was like, "Ooh, I want to study particle physics." And then I like started learning about it. And I was like, "Wait, no, like this is actually not that exciting. You're actually just going to be at a desk doing data analysis if you study these kind of areas." And then I like stumbled onto condensed matter physics as kind of like accidentally, because as I said before, condensed matter has a bad marketing problem where no one knows about us, but it's actually doing an amazing amount of like fundamental research into like finding new states of matter. But secondly, it has these huge number of industrial applications. All of the technology that we've come up with over the last like 100 years has been due to advances in condensed matter applications. Semiconductors are the basis of Silicon Valley technology. Semiconductors were founded at Bell Labs by John Bardeen and Cooper, who were condensed matter physicists just doing fundamental science. And they just came up with semiconductors, revolutionized the entire industry. Same thing with lasers. No one had any idea what lasers could be used for, and lasers are absolutely everywhere. So condensed matter physics as an area to go into has these amazing technological applications. So you could go into this, get a PhD, and then immediately get snapped up by industry because there is a huge amount of need for physicists to do this kind of work. And then talking about how, cross disciplines, one big, huge, advance over the last like 20 years is artificial intelligence, using neural networks, using some sort of, AI to solve really hard problems with a lot of data. Turns out quantum computing and the quantum computers are this perfect match for problems that can be solved using AI. So what you're going to be using is AI software on a quantum computing hardware, and that'll help you solve data crunching problems hundreds of thousands of times faster than anything you could do with even the biggest supercomputers in the world. Google had a computation that they ran a couple of years ago where they did it. They theorized how long it would take a supercomputer to do this calculation. Turns out it was like 1,000 years. They put this exact same problem into their quantum computer and did it in like 0.2 seconds. So if there is a way now that you can translate problems in this classical domain and put it into a quantum computer, you're going to get this huge factor of speed up in solving problems and crunching data. So there is a huge incentive for cross-discipline, working with data scientists, working with computer scientists, figuring out new quantum algorithms. So quantum computing is an area I would recommend a lot of people check out, just because it has this application to industry, to new technology, and to this future of AI.
Perfect. So finally, I would like to ask, what would be your final take-home message from your research? I mean, obviously you have a very good invention in your hand. How would you use that to further your research or for an application?
Yeah. So hard question for me to answer. I am, primarily motivated by fundamental science. I just like figuring out things for, why does this thing exist? And that's like fundamentally an interesting question. And I don't think it has to be interesting, in a technological sense for it to be an interesting question. But I understand, when you're writing grants, you got to tell people why it's important and how it's going to revolutionize the world. And I think quantum computing is one aspect, but another aspect is something called metrology, which is, how we measure things and how do we measure time. It's actually a condensed matter system. It's the number of vibrations of some like cesium atom in a basement somewhere is how we define what a second is. If we now want to use, if we want to measure things to a very precise level, the tiniest changes in magnetic fields for, I don't know, scanning magnetic fields in your brains, doing brain scans. All of these require very sensitive sensors. And quantum states of matter are some of the most sensitive states that exist. And there are groups all over the world right now who are building sensors that use quantum states of matter as their basis. So, we are doing fun science because it's fun to do, and we can do it, and we can get to these temperatures. But, the aspect of doing fundamental basic research is that down the line, it always leads to technological application. Every single major physics theory over the last 150 years has somehow percolated out into the world and are being used by engineers, used by data scientists, used by people all over the world every single day. One example I use all the time is Einstein's theory of relativity was this random, theory that he came up with, had zero application to the real world when he came up with it. And now we're using GPS, global positioning navigation systems, that if we weren't for the calculations done using general relativity, your GPS would be off by kilometers within a couple of seconds, because the satellites experience time differently because of being further away from the center of the Earth than you are at the surface. So all of these weird out there physical theories eventually do percolate into the real world. So if there is a take-home message, I guess it's that. It's just we need to do fundamental science, and we need to be patient with it, because it takes this huge amount of time for it to, to us to go out there and be like, oh, look at that. That has a thread that goes all the way back in time, 40 years to this theory. So the importance and the patience required with doing fundamental research is probably my take-home message for today.
Absolutely. Patience and persistence in research life is a must.
Yep, absolutely.
Thank you very much for sharing those interesting ideas. So before we wrap up, at NcodeX, we have a large community of young researchers and those who wish to enter into research careers, undergrads, and even after O-levels. Mm-hmm. So what would be your advice if someone wants to pursue a career in either in quantum state matter or general in physics? And what would be your general advice for them as a scientist?
Yeah, that's a hard one. I think physics has a reputation that can be intimidating. So I think we lose a lot of good people because at the very start of doing their degree, people are like, oh, the people doing physics are so smart, and I can never do the math that they require. And I don't want people to think that physics is something everyone can do. Maybe you won't find it interesting to do research. Maybe you don't want to actually sit down at your desk or sit in front of a blackboard all day, just pushing symbols around on a page. Maybe that's not for you, but you can do it. So I don't think people should have this idea of physics as this thing that's unreachable, as unattainable. Step at a time. Everything you learn is just about patience. You're not going to learn quantum mechanics in a day. You're not going to learn these advanced mathematical techniques over even a year. It takes patience, and patience with yourself, and being kind to yourself as you go through this process. It's okay to not understand things, but ask questions. Every single person who has done physics has got through because of the help of the community of people around them. I lean on the PhD students before me. I lean on the postdocs. I ask my supervisor of lots of questions, and the fear of appearing stupid is probably the biggest hindrance of becoming a physicist. Something I suffer from all the time. I'm like, oh, do I want to ask this question because they're gonna think I'm dumb because I missed some very basic thing. But getting over that fear is very important. And I truly believe anyone can do this math. It is a cultural thing that prevents a lot of people from going into physics. But if you go through that barrier, if you have patience with yourself and you learn good habits and find your community, I think you'll find a great home in physics. So with anyone hoping to do it, I think you should do it, and I think you should be kind with yourself through the process, and you'll eventually get there.
Absolutely interesting subject, and something everyone can use a little bit of physics, because you will see the world differently when you understand the physics.
Absolutely. Every time I walk out the door, I'm like, ooh, that relates to something I learned about. I can't stop thinking about it. Maybe that's the drawback of doing physics, is like you can't stop thinking about it once you once you start thinking about it.
Absolutely. Thank you very much, Pramodh, for being here with us today. And if anyone would like to get in touch with Pramodh, by all means, reach out to us. We will get you in touch with him. And thank you again for joining with us for the PhD talk in the midwinter, in the late night. Thank you very much. And thank you everyone for joining with us. And we will see you next month from the PhD talk episode 6. Have a good.
Okay, thank you so much. This was an absolute pleasure.
Take care.